Okay, I think we're live. Welcome, welcome back if you've seen this before. Um, this is Bite Me. Sorry, I'm just making sure that I'm live on every platform. Okay, nice. Okay, welcome to Bite Me, where we're squashing bugs one bite at a time. Today we're going to be jumping into common collections in the Rust book, which is going to be chapter 8. We're talking about hash maps, vectors, and our big capital string as well. If you have not been following on the series, you can go back into my lives. The first one will be for chapter 1 and so on and so forth. I'm also creating a Rust mini projects guide so that you could do that after we finish a chapter. It's just going to be going over topics that we've been through in that chapter. Lastly, I thought I had something else to say. I'm not sure. Anyway, I'm having two more. I think it's chapter 6 and 7 are coming out today or tomorrow. So you stay tuned for those. We already finished chapter 6 and 7, and now we're going on to chapter 8. So chapter 8 and I think chapter 9 should be out this week as well. All right. So let's jump in. Okay, common collections. Rust Standard Library includes a number of useful data structures called collections. Now, most other data types represent one specific value, but collections contain multiple values. Unlike the built-in array and tuple types, the data that these collections point to is stored in the heap, which means that the amount of data does not need to be known at compile time and can grow or shrink. We did talk about the heap and the stack within chapter 2. If you haven't seen that live, go back and check that out. But essentially, the heap is more of a growable or shrinkable memory allocation. The stack is a known fixed point of memory. Okay? Each kind of collection has different capabilities and costs, and choosing an appropriate one for the current situation is a skill that you'll develop over time. Now, in this chapter, we'll discuss 3 collections that are used often in Rust programs. A vector allows you to store a variable number of values next to each other. Okay. A string is a collection of characters. We've mentioned a string type previously, but in this chapter, we'll talk about it more in depth. A hash map allows you to associate a value with a specific key. In this particular implementation of the general data structure called a map, I'm pretty sure a hash map is like a dictionary. It's like it has the keyword and then it has the definition. So it's kind of like associating those two together within the hash map. To learn about other kinds of collections provided by the standard library, we can look into the documentation, which is also the documentation that we're reading today. So we'll discuss how to create and update vectors, strings, and hash maps, as well as what makes each special. I'm kind of excited for this one because I don't remember reading this chapter at all. So let's get into it. All right, storing lists of values with vectors. The first type we'll look at is vect_t, also known as a vector. Vectors allow you to store more than one value in a single data structure and puts all the values next to each other in memory. Now, vectors can only store values of the same type. They are very useful when you have lists of items such as lines of text in a file or prices of items in a shopping cart. Now, creating a new vector. To create a new vector, you're going to, or new/empty vector, we'll call it vec::new function, as shown in 8-1. So we're creating a new vector. Let v equal a vector. This is the type, which is an I32, so that's what we're going to be holding within this vector, and we're binding it to this vector new, new, which is creating the vector here. Now, note that we just added a type notation here because we aren't inserting any values in this vector. Rust doesn't know what kind of elements we intend to store. So this is an important point. Vectors are implemented using generics. We'll cover the use of generics with our own types in chapter 10. We did see some generics within the option T that we were learning about within the structs and enums chapters. And that is just one example of what a generic is. We'll be going into depth on like how to do generics and everything like that later on. For now, know that the vec_t type provided in the standard library can hold any type. So we'll create a vector to hold a specific type. We can specify type with the angled brackets. So our type is an I32-bit integer. Now, in listing 8-1, we've told Rust that vec_t is v. In v will hold the elements of an I32 type. Now, more often we'll create a vec_t with the initial values, and Rust will infer that the type of value you want to store. So you rarely need to do this type annotation. Rust conveniently provides a vect macro, which we can create a new vector that holds the values you give it. And listing 8-2 creates a vect I32 that holds the values of 1, 2, 3. The integer type of I32, because that's a default integer type, and we'll discuss the data types in chapter 3. Oh, in the data type section. Oh, as we discussed in data types section of chapter 3. So if you haven't seen data types, chapter 3, go back. I think it is episode 3 or 4, depending on how long the previous section was. I think Guessing Game was 2 parts, so it's probably going to be 4. Right. So here we see let v is bound to a vect macro, which is holding these 3 elements, which is 1, 2, and 3. Now, because we're given initial I32 values, Rust can infer that the type of v is vect I32, and the type annotation isn't necessary. Now, next we'll look at how to modify a vector. Now, updating a vector, to create a vector and then add elements to it, we can do a push method. So this is how we do it. We let a mutable v equal this vector, which is creating a new vector, and then we're over here we're utilizing a method called push and pushing in 5, 6, 7, and 8. Now, as with any variable, if we need to be able to change its value, we need to be able to make it mutable using the mute keyword, as discussed in chapter 3. Now, the numbers we place in all type of I32, and Rust infers from the data, so we don't need a vect I32 annotation. Now, reading elements of vectors. There are 2 ways to reference a value stored in a vector, via indexing or by using the get method. Now, we've done indexing before in previous chapters, and we know how to use dot notation to index, or there's another way that we do with our arrays, is we use our brackets, not the curly brackets, just the regular ones, and that also is able to index into whichever variable that we want to, or whichever vector or array that we would like to. So with indexing syntax, the get method. So here we go. We have a let v bind to a vec macro, which is holding elements 1 through 5. So we know it's going to be typed I32 integer, even though it's not specified there. We let third type as a reference to an I32, and then we're binding that to the v variable that we referenced over here. So we're referencing the v variable, and we're indexing 2. Now print line the third element. Remember that 2 is actually 3 because we start at 0. So it's going to be 0 is 1, 2 is 1, 3 is 2. So we should be indexing 3, the third one. Now let third bind to this reference of I32 and then this reference of v indexing 2, which will be 3. We're print lining the third element, and we're utilizing the variable that we created over here for third. And then it says let third, and we're typing it as an option. Remember, we were learning options in the previous chapter. Option reference to an I32. Okay, so I'm pretty sure right here we are shadowing the third variable that we just created, and we're utilizing it here by binding it to v.get2. And now we're matching, which we're using a match statement on third. So sum with third as a parameter will print line the third element is third. Now none is going to be print line that there is no third element. So let's run this. Let's see. It should print sum, yes, and it should print this first line because this is before it. An order of operations, when you're doing anything in the main, it's going to print the first thing first. So if you do a print line up here, and then you do the same print line down here, it's going to print both of them because this one came out third, then we had this option reference to an I32, and we're matching on third. Or sum. We're matching on sum, which has an argument of third. Now note that any decals here, we use the index value of 2 to get the third element because vectors are indexed by numbers starting at 0. Now using the ampersand and the brackets gives us a reference to the element at the index value. When we use the get method and the index passed as an argument, we get an option t, or option reference t, that we can match with. Now Rust provides these two ways to reference an element so that you can choose how the program behaves when you want to try to use an index value outside the range of existing elements. An example, let's see what happens when we have a vector of 5 elements and we try to access an element at index 100 with each technique, as shown in listing 8-5. So we have let v bind to this vect macro, which is holding 1 through 5. Now let does not exist equal a reference to this index number of 100, which is not within our range. Then we have let, we're shadowing this previous variable down here. So let does not exist equal v dot get, and then I guess this now we're pushing, or we're getting 100. So I'm pretty sure what it said over here. Get to, okay, so get to is also so we're indexing in both scenarios, my bad. So we're indexing with the get method, and we're also indexing with our index method, with our brackets. Now, this code will panic. You see how it's all confused? It usually will tell us if this code is going to panic or not, because we don't have an index of 100. So even if we run this code, I'm pretty sure it's not going to have any outcome because there's no print line statements to the terminal. But even if we run this code, it's going to give us a big compile error telling us that we do not have these indices, okay? When we run this code, the first bracket method will cause the program to panic because it references a non-existing element. Now, this method is best used when we want your program to crash if there's an attempt to access an element past the end of the vector. Now, when the get method is passed, an index that is outside the vector, it returns none without panicking. You would use this method if accessing an element beyond the range of the vector may happen occasionally under normal circumstances. So remember when it showed us two different ways to index. So it also had this match statement, and this option I32 gives us the example of how when we go outside that range of that index number, let's say we have only 5 elements within our vector, we go outside that range, instead of it crashing and panicking, what it does is it prints this line instead. So if this was index 100, and we know that we cannot index, or this is index 100, we know that we cannot index 100, it's going to tell us the non-print line statement that there's no index 100 element, okay? When the get method is passed, an index is outside the vector. It returns none without panicking. So you would use this method if accessing an element beyond the range of the vector may happen occasionally under normal circumstances. Your code will then have logic to handle having either some reference to an element or none, as discussed in chapter 6 when we're talking about the option T. Now, for example, the index could be coming from a person entering a number. Now, if they accidentally enter a number that's too large and the program gets a none value, you could tell the user how many items are in the current vector and give them another chance for them to enter a valid value. Now, that would be more user-friendly than crashing the program due to a typo. And we have a lot of these testing checks that we do before we deploy our programs, so that in the event that somebody does do something wrong by accident, it doesn't panic and then shut down or not compile at all. Okay. So when the program has a valid reference, the borrow checker enforces the ownership and borrowing rules covered in chapter 4 to ensure that this reference and any other references to the contents of the vector remain valid. Recall the rule that states that we can't have mutable or immutable references in the same scope. The rule applies to listing 8-6, where we hold an immutable reference in the first element in a vector, and try to add an element to the end. Now, this program won't work if we try to refer to the element later on in the function. Let's look at this. Look, he looks very confused. So it says, this code does not compile. We have a let mutable v equal a vector macro, which is holding 1 through 5. Then we have let first bind to a reference to v, and we're indexing 0, which is 1. Remember, we always start at 0. Then we have v.push, and we're pushing this letter 6 onto here. I mean, this number 6 onto here. Now we're going to print line the first element is first. Now compiling this code will result in an error. So we have an immutable borrow occurs here. Mutable borrow occurs here. And the first element of first is an immutable borrow that are used here. So this code in 8-6 may look like it should work, but why should a reference the first element care about changes to the end of the vector? Now this error is due to the ways vectors work, because the vectors put the values next to each other in memory. and adding a new value to the end of the vector might require allocating new memory. And copying the old elements in the new space if there isn't enough room to put all the elements next to each other where that vector is currently stored. In that case, the reference to the first element should be pointing to the deallocated memory, and the borrowing rules prevent programs from ending up in that situation. Okay. Essentially, what I'm inferring as to what they're trying to say is that we are trying to utilize this original variable that has the vector of 1 through 5 in it, and then pushing 6 onto it when it needs to be allocated in memory next to each other. So the vectors have to sit next to each other in memory. But then we're going back to utilizing this first element, let first, which only has 1 through 5 on there, when we already tried to mutate the current mutable variable v by pushing 6. So it's just not going to compile correctly because it doesn't even know we're not even utilizing this correctly. It's not putting it next to each other. I think that's what it's trying to say. It says as we're copying the old elements to the new space. If there isn't enough room to put all the elements next to each other where the vector is currently stored. So because it's stored on the heap, it's a bit different. That's interesting. I didn't actually know that. I didn't know that about vectors. Okay, iterating over the values in a vector. To access each element in a vector in turn, we would iterate through all of the elements rather than use indices to access one at a time. And listing 8-7 shows how to use a for loop to get immutable references to each element in the vector. I don't know if we ever went into detail about loops. I feel like we went briefly over what loops are, maybe common programming concepts, but we never really went into detail about loops and for loops. Essentially, they're what you use a for loop is you're iterating through a collection. So this is a vector, which is a collection of data, and we're going to be using, in this case, this for-i. I is considered an element within the collection. So for an element in this collection, which is a reference to this variable v, print I. You can see over here, let v equal this vector. We have 100, 32, 57. So it's going to iterate through every single one, and we want them to print 32, and 57 within it, in which it compiles perfectly fine. That's how for loops work. You can go back to chapter 3, and then it talks more about loops. Then we have a while loop, for loop, and just a regular loop. We do use loop within our guessing game. If you saw the guessing game that we created in chapter 2, it shows you how to use loop and how to break out of it as well. So. We can also iterate over immutable references to each element in a mutable vector in order to make the changes to all elements. Now the for loop in listing 8-8 will add 50 to each element. It says let mutable variable v equal a vect macro, and it's going to have 132 and 57 within it. Now for I, which is an element, so let's break this down. For an element, which is I, in this mutable reference v, which is this, So we're referencing this. It says, I don't know what this is. Oh, I think this is just a multiply. No, this is a dereference. This is a dereference. Dereference I, and then plus or add 50. Okay? So this should be 150. This should be 82, and so on and so forth. Okay? So let's see if this will run. Okay, there's no output because there's no print line statement. But to change the value in the mutable reference refers to, we have to use a dereference operator. And this dereference operator always goes over my head, so I hope to go into depth very soon. We'll talk a little bit more about the dereference operator section in chapter 15. So it's a little bit of ways away, but iterating over a vector, whether immutably or mutably, is safe because the borrow checkers rules. If we attempted to insert or remove items from the for loop bodies in the for loop bodies in listing 8-7 and listing 8-8, we would get a compiler error similar to the one that we get with the code in listing 8-6. Now the reference to the vector that the for loop holds prevents simultaneous modification of the whole vector. Okay, yes, I understand what it's talking about. So we actually use this mutably, this reference to a mute v over here in this one. We didn't put a reference to a mutable variable. We just put reference v. So we didn't know it was going to be mutable, like mutated. And then here we added something, so we did mutate this reference, this variable. You know what I mean? And this is why it won't compile, because we're doing two things over here. We're doing something that's supposedly immutable. We're just referencing it, and then we're pushing to it. So we're appending it in some way. Oh my god. I already read that. Using an enum to store multiple types. Now, vectors can store multiple values of the same type. This can be inconvenient. There are definitely cases for needing to store a list of items of different types. Fortunately, the variants of the enum are different under the same enum type. But when we need one type to represent elements of different types, we can define and use an enum. Okay. For example, say we want to get values from a row in a spreadsheet in which some of the columns in the row contain integers. Some floating points, some strings. Now we want to define an enum whose variants will hold different values, and all the enum variants will be considered the same type, that of the enum. When we create a vector and hold that enum, and so ultimately hold different types. We've demonstrated this in listing 8-9. So we have an enum called spreadsheet cell. It has an integer, which is an I32 integer, a float, which is an F64, and a text, which is a string. So it's holding that these different types within the enum. Okay? So we have let row equal a vector, and we are calling our enum, which is spreadsheet cell, and utilizing the variance in integer or int, which is 3, text, which we use from string, which is blue, and float, which is 10.12.
Now, Rust needs to know what types will be in the vector at compile time, so that it knows exactly how much memory on the heap is needed to store each element. Okay, so there must be explicit blah, blah. We must also be explicit about what types are allowed in this vector. Now, if Rust allowed a vector to hold any type, there would be a chance that one or more of the types would cause errors with operations performed on the elements of the vector. Now, using an enum plus a match expression means that Rust will ensure at the compile time that every possible case is handled, as discussed in Chapter 6. Now, if you don't know the exhaustive set of types a program will get at runtime to store in a vector, the enum technique won't work. If you don't know the exhaustive set of types types a program will get at runtime to store in a vector, the enum technique won't work. Instead, you can use a trait object, and we'll cover that in Chapter 18. Now that we've discussed some of the most common ways to use vectors, be sure to review the API documentation for all the many useful methods defined in Vector T by the standard library. For example, in addition to push and pop method removes and returns the last element. Okay, so dropping a vector drops its elements. Like any other struct, a vector is freed when it goes out of scope, as annotated in listing 8-10. Okay, here we have this vector that we created over here that we're doing stuff with V. V goes out of scope, it's free. Easy. Okay, when the vector gets dropped, all of its contents are also dropped, meaning the integers it holds will be cleaned up, and the borrow checker ensures that any references to contents of the vector are only used while the vector itself is valid. Let's move on to the next collection type, which is the string. So I was supposed to do this. This is going to be a pretty short live today because I was supposed to do this on Friday so that we could jump into Chapter 8 and have a little fun with our vectors. But today I'm kind of just catching up. I usually don't record on Mondays. Here, let me go up here. I usually don't record on Mondays, usually at all. So these are my off days. So I wanted to do a short live just so that I can catch up from Friday. Tomorrow we're going to be doing 8.2 and 8.3. We're going to be going through all of this. So that might be a pretty long live. I just want to get on here before it starts storming and let you guys know. Today was a great live. I thought I had a lot of fun. I usually have fun on these lives. I love to just learn, and I love to help people learn as well. If you are watching on Twitch, you could definitely look at my YouTube, which is also called Bite Me. We have previous lives on there if you want to go back. I just started streaming on Twitch, so I don't have many lives up or any reruns up that much. So go and check that out. You can also check out my Rust Projects miniseries, and that is going to be leading or following the Rust book that we're reading. So if you want to check that out as well, stay tuned for Chapter 6 and Chapter 7. They'll be coming out tonight or tomorrow. And I'll see you tomorrow on our next live. Bye.